Orbital Gardens, this is Mission Control. We are confirming acquisition of your signal. You are live in 5, 4, 3, 2.
Hello and welcome to Gardeners of the Galaxy, the podcast for all of the sentient beings in the universe who have a passion for plants. I am Emma the Space Gardener and I will be your host as we explore gardening on Earth and beyond. While I've been working on this episode, people all across the United States have been planting their moon trees, a new generation of trees grown from seeds that flew all the way to the moon on Artemis 1. Boeing's Starliner made it all the way to the International Space Station for its crew flight test, and some issues with the propulsion system mean it's still there. NASA is suggesting it won't now return until July, and Butch Wilmore and Sonny Williams have until the 20th of July before their ride turns back into a pumpkin, as Starliner can spend up to 45 days docked with the space station. Our mission specialist for this episode is Borja Barbero Barcenilla, a postdoctoral researcher at Texas A&M University. Borja has been working with Dr. Dorothy Shippen to explore the effects of spaceflight on plant telomeres. Before we get to that, I'd like to thank each and every one of you who supports the show, whether that's via a financial contribution or by sharing it with friends and colleagues. Gardeners of the Galaxy wouldn't exist without you. And if you haven't already discovered the Gardeners of the Galaxy Mission Report, it's a weekly email newsletter packed with astrobotany news and updates. To subscribe, visit theunconventionalgardener.com and click the newsletter link in the top right corner. Hello Borja, welcome to Gardeners of the Galaxy. It's great to have you on the show today.
Hey Emma, how are you doing? Very happy to be here.
So I'm really excited to be talking to you because you've been doing some really fascinating work with plant telomeres. So maybe you could start us all off by explaining what telomeres are.
Yeah, so telomeres are basically the DNA repeats at the end of the chromosomes. They do not code for protein, and their major function is the protection of the whole genetic material. One very simple analogy to understand what telomeres are, it is looking at the shoelace.
Okay.
So in the very tip of the shoelace, you have what is called the aglet, which is the metal plastic thingy at the end of the shoelace that protects the integrity of the shoelace. If you lose that part, you start seeing that the shoelace starts disintegrating somewhat. So that is what telomeres are, like protecting physically the chromosomes from being eroded and degraded.
Okay, so what made you start thinking about what telomeres would do in space?
So that is actually a very long question. I guess we have some time to discuss this, right?
Yeah.
But, so the project started quite funny as I think we all read the twin study experiment and we were amazed by the results that came up. One of the bigger results that there was that telomeres elongated in astronauts in the International Space Station. So that was quite shocking to us. So when telomere length changes, it is associated with bad things. Telomere shortening can lead to early senescence, and that's one of the reasons why we age. And telomere lengthening is a hallmark of cancer cells.
Okay.
So you really want to have your telomere length in some sort of range, which is like a yin and yang. Too much of it is bad, too short and is bad as well.
Okay.
So it was quite fascinating to see that the telomeres got longer in space. And at that time, I was a graduate student in the Shippen lab. Dr. Dorothy Shippen, she is the queen of plant telomeres, on the Earth, and she was good friends with Susan Bailey, which is one of the PIs from the twin study experiments, and combined with Chris Mason, one of the people that did the telomere length analysis on astronauts. So Dr. Shippen reached out to Susan Bailey. He's like, hey, has anybody looked at plant telomeres in space? And the reason why people should look at telomeres is because they are markers. They are markers of how long an organism will be able to be prosper, right? So if you have organisms that have lower telomeres, they often have lower chances of species prosperity. So if we're going to go interstellar, we need to make sure that the plant telomeres are in a good range because, as you know, many of your people that have come here in this fantastic podcast has mentioned that we're going to need plants for multiple generations to grow them. We cannot keep resupplying space missions with ramen noodles and dehydrated food, so to speak, right? So we're going to need bring plants with us. So the question was that, Susan Bailey is like, nobody has done anything about plant telomeres in space. So she reached out to NASA Gene Lab. So she reached out to Ryan Scott, and basically Ryan Scott put us in contact with Richard Barker and Colin Cruz, that they were the plant AWG directors at the time. And basically they had a NASA Plant Gene Lab meeting, and they raised the question, hey, researchers at Texas A&M, they're looking for if anybody has samples, flown samples, that they can look at telomeres in space. And then Dr. Sarah Wyatt and Dr. Imara Pereira jump in, hey, we have an upcoming flight, and we're going to have tissue left over from all of that. So that was how it started as well. And I have to mention that one of the people that asked that we should look into it was an Argentinian physicist that has previously worked on the physics of telomeres. So quite an interesting hypothesis he had, reaching out like, you guys should look into this. And then we reached back to Gene Lab. And I just have to say how amazing it is to have a group, a big group at NASA that are looking to help and collaborate with as many scientists as possible, which is something very, very positive that happens there. And then Dr. Wyatt took us as part of the team, and then we were there for the launch and everything. Samples came back, experiments happened. We published last year in Nature Communications, one of the earlier studies. So like the paper has had a lot of recognition already, so we're very pleased with that. And now we got the grant in 2022 to bring telomere-associated mutants to the station. I don't know if we'll talk about that, but we're currently in the midst of a new exciting study with more researchers, which is quite fun.
Okay, so we'll get on to those sort of upcoming things in a minute. I mean, it was quite a fun story, really, because you sort of piggybacked on somebody else's research. That was Apex 07, wasn't it, with Dr. Wyatt and Alexander Myers?
Yes, absolutely. So I literally tag along with them. They took me as part of the team. Dr. Wyatt is a fantastic person. Dr. Myers, he is so much fun. I love discussing science with them. And they were so nice, so keen. It's like, what do you need? And then there was the issue that some of the plates were left up in the station, that they couldn't find them. I had, to this day, one phone call from Al the day of the sample return, right?
Yeah.
He gives me a call. It's like, hey, there's a problem. We're missing 50% of the plates. It's like, what do you mean we're missing 50% of the plates? But they are nowhere to be found. It's like, okay. Well, and the good thing that came out of this NASA was very nice. They did another launch, which was in December. So the beauty of this, we were able to perform some extra experiments that we were hoping, just because there were some extra tissue. So that was quite nice. I think that's what made the paper even better. But, making the best out of a bad scenario kind of thing. And it worked fantastic. Yeah,
it's amazing. So, I mean, with your paper, what did you see with the telomeres? What happened to them in space?
So before our paper, every organism that has been in the International Space Station saw that telomeres were elongated. And this was tested in both C. elegans and in humans, and in different cohort of astronauts this was performed. So we were hoping to see probably telomere elongation, especially because I remember to this day, Al came here to do the experiments. The first experiment that we did was telomerase activity. And the reason why we did telomerase activity first was because telomerase activity had never been done in space. So one of the reasons why telomere could get longer in astronauts is because the enzyme telomerase that is in charge of having telomeres could be hyperactive. Okay. However, the protein samples were lost for all of those experiments, and telomerase activity had never been done. So we wanted to be, probably one of the first people to look at telomerase activity of samples that have been in space. And we saw that telomerase activity was very high. And we were like, wow, that's amazing, like over 50-fold, which in Arabidopsis doesn't happen often. And then it actually came to be even higher as we continue to do more samples, over 150-fold telomerase activity increase. So we expected to see, okay, there's going to be telomere lengthening happening, and we're going to be able to explain exactly what happens to astronauts, like telomerase activity induces linked to telomere elongation.
Yeah.
And we see a week later, the telomere length analysis, no change whatsoever of telomere length. And at first I was kind of shocked. I was like, what in the world? It's like, how there's no changing with that much telomerase activity increase? Yeah. And at first I was like, kind of, I don't know, it came like sadness because my hypothesis wasn't there. But then I was like, this is much cooler, actually. You are seeing a a differentiation of function of telomeres, that telomeres activity increase is not leading to telomere lengthening, which in humans is almost a direct correlation, right?
Yeah.
So that was the shocking thing. And the positive news about this is that Arabidopsis, in this case, was able to maintain telomere length homeostasis, which is very important. Telomere length changes, as I explained before, is not good. You don't want it shorter, you don't want it longer. So be able to maintain telomere length at the proper length, it is a positive that we observe from this, that plants might be best suited than other organisms to withstand this space telomere length changes.
Okay, so I mean, there's obviously a lot more work that needs to be done there before we understand what's happening.
Exactly.
But you published a paper earlier this year about some ground-based research that you've done with Arabidopsis again, using simulated lunar regolith. So can you tell us about that?
Yes. So, I think we were all in awe with Annalisa Paul, and you interviewed her here in the podcast with the fact that she was able to grow Arabidopsis using genuine lunar regolith. That was fantastic. Amazing. And awesome.
Yeah.
Yes. So, we were motivated by that. And the question was similar. Are these plants going to be able to grow in this lunar regolith? In our case, we're using lunar regolith simulant for multiple generations. And if so, what's going to happen to their genome? And what we observe is that plants that are grown in lunar regolith simulant, they display telomere shortening. Okay. And this is apparent in the first generation. And then in the second generation, there's even a further shortening. And this is just using Columbia wild type. So that is not good news to us, because that means that plants are going to suffer from loss of genome integrity while they're grown on the lunar regolith simulant. Obviously, the question remains whether this will happen in genuine lunar regolith. And we tested different ecotypes and as well as different lunar regolith simulants that they were all provided by Exolith Lab. And we saw that telomere shortening happening in all of these different ecotypes and using different regolith simulants. However, don't worry, there's good news for humanity. And one of the things that we're going to have to do as plant scientists is come up with the correct genetic makeup of plants that will be able to sustain growth in lunar regolith as well as radiation and other damages. But we're seeing that different modifications in antioxidant machinery and telomere-associated components is leading to plants that do not suffer from that telomere loss as they're grown in the regolith simulant. So, which is good, and is something that maybe at the last question I will say what kind of plants we're looking to grow in the moon. Is plants that will be able to maintain their telomere length during multiple generations. So that is we're collaborating with different people to see if this is happening in crops as well, because, Arabidopsis thaliana is not a plant that you want to eat. You could eat it, but I don't think it tastes very good. No. Maybe, and Arabidopsis salad is not a real thing yet. So we're testing the same to see if we see the same phenotype in different crops with different labs. Florida Tech, at Winston-Salem University, and here at A&M as well. So to see what we see.
Okay, I mean, it's not a particularly surprising outcome, maybe, because, I mean, Annalisa found in her research that the plants were very stressed when they were grown in the genuine regolith. It was not nice for them at all.
Yes, exactly. So she observed that there was oxidative stress happening in those plants. And one of the reasons why telomeres could shorten is due to increased oxidative stress. And that's exactly what we saw as well. We saw that the genome oxidation of this plant was quite high. So we need to find plants that do not have as much genome oxidation once they're grown in these conditions, right? And another thing that I would like to capture is why, I got asked this question quite a bit. Why is this important? Why do we need to keep growing plants in lunar regolith simulant? Well, we're going to learn quite a bit from this. And one of the things that we're going to learn is to cultivate plants in soils that are terrible, so to speak.
Yeah.
So the more we're able to grow plants in these conditions that are very harsh to plants, the more we will learn to cultivate the same type of plants in here on Earth where the conditions, we're not making things better, so to speak.
Sadly, yes. Okay, so, I mean, you briefly sort of mentioned the radiation in space that plants are going to have to cope with, and you're working on something with space radiation and plant telomeres now, aren't you? You've been on a very exciting visit to Brookhaven National Laboratory. So that sounds exciting. What's that about?
Yeah, so it's part of our new grant that we got funded in 2022 by NASA, which included a Brookhaven trip, included a flight to the ISS, and then as well as Brookhaven time. So what we are testing over there, it is a follow-up from our last experiment to see what levels of radiation are leading to telomerase activity increase, plant genome oxidation, but it as well is under the same umbrella, whether plants will be able to maintain their genome integrity with radiation, with increasing amounts of radiation. So yeah, we were at Brookhaven a couple of weeks back, me and Emma Kennedy from a graduate student from the CIPN lab, and we performed experiments in which we radiate different Arabidopsis mutants, a very cool mutant as well that maybe I'll get to talk about later, that are involved in the oxidative stress response as well as telomere-associated components, and see what is the effect of these plants after they have been hit with different sorts of galactic cosmic ray radiation. And the Brookhaven trip was awesome. It was so cool. Just go over there. You know, when you go into the radiation room, you have to have your iris scan. And, you know, it feels like you're walking into Terminator, iris scan in and out. Keys have to turn in at the same time as your iris scan is going. The people at NSRL and BNL, they are fantastic. The most accommodating people, so helpful. The whole experience was awesome. It was nice. And we are currently actually now doing the experiments, and we're starting to see some very interesting preliminary results from all of this. And hopefully as well, we will have the flight coming up soon, but we can talk about it a bit.
It's exciting actually, because when I was doing the prep work for this, and I looked up what you were doing at Brookhaven, and you went to the NASA Space Radiation Laboratory, and
yes,
and it's basically a big particle accelerator, isn't it?
Yes, exactly. So what happens is there's a big particle accelerator, and your plants are at the end of it. You know, we all have seen science fiction movies in which the particle accelerator, they do crazy stuff. And, you know, I never thought that I would put my plants at one end of those and then pick them up and see what was the effect on the genome. So that was quite interesting.
Okay, so you were talking then about a cool mutant. So your Arabidopsis strain that does something amazing. You wanted to talk a bit more about that?
Yes, so it is obviously not published of any sort, but have you heard of tardigrades?
I have heard of tardigrades. Tardigrades are awesome.
Yes. So there are a couple of proteins in tardigrades that make them more resistant to radiation. And in reality, what they do is they protect the DNA from getting oxidized from different sources and protects the animal from the dangers of desiccation.
Yeah.
So we were able here in the CIPL lab to put a tardigrade protein into Arabidopsis. Oh, wow. We have been able to express it. And we're looking to see if this tardigrade protein in Arabidopsis can protect the plants from the effects of radiation.
Wow.
So that's something that we're very interested about, and hopefully it turns out something quite interesting for plants.
That is amazing. That is so cool.
Yes.
And you also said that as part of this grant, you've got a flight experiment coming up?
Yes, so we were going to use a hardware called Spectrum. So we're going to be the second group of team to use it. Unfortunately, Spectrum is not operative right now in the station. So we're going back to Beji. So we're going to be Apex 12.
Okay.
So we're going to the Beji, and we're going to have different Arabidopsis mutants. We're going to have this tardigrade mutant, and we're going to have as well antioxidant overexpression plants. So we expect to see that plants that overexpress antioxidants are able to perform better in the International Space Station, meaning lower genome oxidation. And plants that are mutants of telomeres. Remember, I told you that telomeres was highly upregulated in the station in Arabidopsis grown plants. We're bringing a telomeres mutant up to the station, which will have no telomeres activity whatsoever. We expect those plants to suffer much more if telomeres is important for plants to be able to grow happily in the International Space Station. These are basically a follow-up from the telomere studies from Apex or 7, in which we hope to start to understand what is happening in the station, why do you need telomerase activity, and how can you bring that genome oxidation down. on plants by perhaps enhancing antioxidant machinery and as well enhancing telomerase activity. So we're bringing telomerase mutants. We're bringing plants that have already a high level of telomerase activity. So we expect to see already like what are the mechanisms necessary for plants to be able to grow well and display less ROS on the International Space Station with, I guess, hopeful looks at, beyond low Earth orbit activities.
Yeah. Okay. So what sort of timescale are you looking at for a flight?
So we hope to get in a flight by the end of the year or beginning of next year. That's because that will be at the same time that we're finishing, almost wrapping up with the Brookhaven studies.
Yeah.
So, NASA is very busy. There's a lot of experiments, but we're hoping to get in a flight by the end of this year, beginning of the next one. So we will probably be going in July already to Kennedy to start, the GBT, SBTs, and all of these sort of
all of the pre-flight
activities.
Stuff. Yeah.
Yep, exactly.
Oh, you're going to be busy this summer then.
I'm going to be very busy. Yes, I'm going to be very busy. That's why, as we're recording this here on Memorial Day, after this, going back to experiments.
At the moment, we're just moving into a period when researchers are going to be able to go into space with their experiments. Is that something you would like to do?
If I would like to go to space?
Yeah.
Oh, absolutely. But my wife says no. Especially, reading of all the research in astronauts with the telomeres going very, very wacky. And, I explained all the effects that happen when telomeres can change. She says, so you tell me all of this, and then you want to go into space? I say, hey, that's why we're looking for countermeasures. That's why we're looking for things that can maintain your genome integrity better. And I honestly think that one of the ways to countermeasure this will be through plants, right? Use plants as a way to mitigate radiation responses. So, finding plants that are nutrition and protective at the same time. One quick thing that I want to mention.
Yeah. The
project that we have with DSAP, it was previously shown in humans that if you add DSAP to human cells, it will reduce the levels of radiation. So I wonder, if our plants that have the tardigrade protein added into them, if you could eat that plant and already have this tardigrade protein in your organism to protect from the levels of radiation, right? So there's many things that are going to have to be done for the next upcoming space missions to be safe from a health point of view.
Yeah.
The amount of radiation that will be happening on a Mars mission is going to be higher than what it is proposed a human can endure, right?
Yeah.
So we're going to need to find countermeasures to do that, either physically or biologically. So I think that's why plants are so important in space for many multiple reasons that you have covered beautifully in the podcast. But now we have to start thinking them as countermeasures to reduce the amount of damage that humans and astronauts will experience during the space missions.
Yeah, absolutely. Okay, so one day in the future, when we've solved all of those problems and you're allowed to go into space and you're going into space for quite some time, and you're allowed to take one plant with you as your personal sort of your house plant, your pet plant. What would you choose to take with you and why?
So obviously I have two answers to that. Okay. One of them, it is my scientific answer that I have to give, which is a plant that has been genetically modified to endure those levels of radiation. If I want to bring a pet plant, I don't want it to die very quickly. So I'm going to have to enhance it with the correct telomere-associated components and antioxidants to make sure the plant is happy and I can have that pet plant for a long time. But the second one, which is the questions that you often get, which are the cool fantasy plants, I will bring what is called padron peppers. Have you ever eaten a padron pepper?
I have. No, actually I have, because I've grown them.
Nice.
I grew them specifically because, they're Spanish peppers, aren't they?
Yes.
And they have a bit of a trick up their sleeve, because they can be very mild or they can be scorching hot.
Yes, that's why you have to eat the very tip first. to see if you should proceed with the rest of the pepper or whether it's going to ruin your nut. I have them growing here in Texas right now, so I'm very happy that they're finally growing.
Yeah.
But yeah, they are delicious peppers. And then I'm motivated white peppers. I think one of the happiest pictures that you will see of astronauts, it is after APH3, I think, when they grew the peppers. Was it APH3 or 4?
I think it was 4 with the peppers, because 3 was delayed. We've just had 3. 3 was Arabidopsis, Annalisa Poole doing her multiple generations in the epigenetics. So I think it's 4. I think it's 4.
Yeah, so APH4, and you see the astronauts, eating the peppers like beautiful tacos, and you could see their face of happiness. And because I guess in space, food is really bland for multiple reasons. Like, I guess you don't really taste some of the things. So I think having a padron pepper with you when you're on a lunar mission could be amazing. Besides, you put them with a tiny bit of salt and a tiny bit of olive oil. We'll have to bring olive oil. I'm from Spain. We have to bring those.
Yeah.
And it's like something like you've never tried before. And it's just pepper, salt, and olive oil, right? And it's just, oh man, I really want to go back to Spain now.
I have to say that peppers are one of my favourite plants. They are so beautiful. They're little starry white flowers. And yeah, they are really great. But padron peppers are a bit iffy because I'm not good with the chili. I'm not good with heat.
Yeah, but let me tell you something. We have here in Texas, I grow jalapenos as well. My wife grows jalapenos. She takes care of the garden back at home. I have too many plants here to take care of in the lab. But the jalapenos are the plants that they always do way too many. They produce a lot of them, right? Because the birds will not eat them, right? And then there's too many jalapenos. I don't know what else to do with them. I try to come up with interesting recipes. I add them to gazpacho before, jalapenos and gazpacho. For Spanish people, this is a sacrilege. But, I have to give it a try. It was spicy. I was sweating. And, But peppers are fantastic crops to grow on these space missions for many different purposes.
Yeah, they are brilliant. Okay, so we can have your padron peppers in our space greenhouse and our tapas evenings where we're slightly, eating through them with trepidation, trying to see who's going to get the hot one.
Oh, can't wait. Then I might be able to convince my wife to let me go if there are tapas on the space station. Maybe she comes along as well.
Okay, so thank you, Borja, for coming on the show and talking about your research. That's absolutely fascinating, and I'm looking forward to seeing your experiment going to space.
Thank you very much, Emma, for your time, and thank you very much for everything that you do for the Spaceplant community. It is great hearing your podcast, and I can't wait to see who you bring next on the show.
Brilliant, thank you. Thanks again to Borja for coming on the show and sharing his fantastic astrobotany projects with us. Don't forget that you can find the show notes on the website at theunconventionalgardener.com. You can also sign up to the Gardeners of the Galaxy newsletter for new episode alerts and bonus astrobotany content. That's it for this episode, so I'll hand you back to Mission Control. Capcom, do any of the boffins have an idea what that awful whiff is?
Orbital Gardens, this is Mission Control, confirming termination of your signal. We have spoken to the engineering team about the smell you've reported, and they have requested that you try stirring the WC tank. Mission Control out.